Electromagnetics for EM wave propagation. So you learned Maxwell's equation. When you look at very carefully, electrical field is going to cause magnetic field, and the change of magnetic field causes electric field again. So there is a feedback between electrical field and electric field and magnetic field. So how do they work it out when there is a change in the electric field in the space? Okay, it's going to emit EM wave, electromagnetic wave. Okay, so how does this work? Let's look at from Maxwell's equation. Okay, Maxwell's equation we know is this dd over dt is curl H. Okay, so electric field cause magnetic field. If we take a derivative on the time, so it's become second derivative of electric field cause the magnetic field. Why take the second derivative? Because we want to see the change of magnetic field, because the Maxwell's another equation shows the time variant magnetic field causes electric field. Okay, so magnetic field change causes electric field. So if we take another curl on this, so it's going to be this guy. So this is going to be H and another delta here. So it's going to be double derivative of electrical field. So electrical field vectors double curl can be expanded to this minus this. Okay, the divergent, this is divergent electric field, is zero because there's no charge in the space, no true charge in the space. Okay, so we get ultimately the differential equation for electrical field, and this is the differential equation how the electric field behave in the space. We solve this differential equation, we know what the vector E look like, and here's a constant, and c square, the c is defined by this, and when it's a vacuum, it's going to be 0 here. Okay, so this happened to be the light speed. So that was a surprise by Maxwell. Maxwell tried to solve the equation for electric field and magnetic field interaction and came up with a light speed. Of course, nobody knew why. Okay. Now, how can you really solve this one? You need to have a certain boundary condition to integrate, right? So suppose you have an antenna. This is antenna, and you give a current go up and down. This is capacitor. So you charge up, discharge, charge up, discharge. So current keep going. When it's charged up, we learn this by Poisson's equation. It creates electric field. So it's a spherical electric field. Okay, and we make this like a sinusoidal waveform. Then the solution will be this we cover this in the wave and oscillation and the waves chapter of the physics. Okay, there is an attenuation factor. As the wave goes distance, the wave amplitude become less. Of course, it's energy spread in the space, so each section of the space has less energy density. And speed v, that's gonna be the light speed. So this is a frequency. You can have some phase. As usual, you plug in this anticipated solution to this equation, then v becomes c. So you know the wave speed is c. Okay. Now, if you look at this antenna configuration, when E goes up and down like that, the H is generated. Remember the Maxwell's law? The magnetic field generated in a circular fashion orthogonal to I, so it's going to be orthogonal to E. So what happened is EM wave is going to propagate this way. This electrical field that generates magnetic field. The electric field goes negative, the magnetic field goes negative, and it goes up like that. So this is for electric field. We can have similar equation for magnetic field. Only difference is the orientation of vector. The vector is going to be orthogonal. E and H vectors are orthogonal. Okay, and that's the way it's propagated. Okay, now is this the wave? Here's a big question. The wave conventionally, like a water ripple, the water surface ripple around, this kind of wave needs medium. Medium is water, right? And the speed of the wave is a function of medium. Okay, look at this equation. It's not exactly the function of medium. It's pretty much constant. And that was a big controversy of EM wave. Why EM wave speed is not affected by medium? It's consistent. Okay, and so that's kind of supporting argument to later Einstein's special relativity theory. Somehow the light speed is constant. And by the way, the Einstein theory is not about light speed. He merely said there is a maximum speed the matter can go. The maximum speed, light happened to be at that maximum speed. That's what it's about. The Einstein theory talk about maximum speed, and he discovered that maximum speed using light, and this is supporting this. The EM wave goes at the light speed, and so Einstein's theory is not about light speed, about the maximum speed. Okay, so you know how this propagate. This is a propagation, and it's radiate in the spherical fashion, all direction, and it's attenuate by the distance r. Okay, how the EM wave works. Now we look at the energy that each EM wave carry. EM wave is a quantum. So not like water wave, we can identify single wave like a photon. Okay, so single wave carry energy, and if you have many photon, then it's called intensity of wave. But single wave carry energy. That energy is defined by Planck constant and speed over wavelengths. If you plug in Planck constant and speed, then use this micrometers wavelengths, then we can find out electron volt energy level. Okay, now since the speed times wavelengths, no, frequency, wavelengths times frequency, let's say f, is the speed. We plug in this one, it's going to be frequency. So energy increase as frequency increase. That's the EM waves characteristic. Okay, but this energy is a single wave's energy, and this is the big difference between the conventional wave and the water ripple. Each quantum carry certain energy. Of course, you have many quantum. You shoot the flashlight, then you send a lot of energy. That's number of photon times E, and that's the way it works. Why it's important? Well, when you hit EM wave to the material, okay, inside has a molecule. Molecules has a bonding, electron bonding, and this is stable state. It's like electron doesn't get out anywhere because it's stable. It's energy potential like this. And when photon hit, this get excited. Excited means absorbing energy. Then it may move around, but is this energy sufficient to move out this electron bonding orbit? And that's what this is going to be important. Okay, if E is larger than E prime, then EM wave is going to change the molecule, because when it's hit, most likely these electrons go out of orbit and this chemical bonding breaks. Okay, so the higher frequency, the EM wave possibly change the molecule. Okay, but that's happen only when it's really high frequency above the visual light frequency, when it goes to from visual light to ultraviolet and X-ray and gamma ray. Those are high energy beam. Why it's high energy? Not because there are many particles sent. It's because each electron carry so much energy, and when it's hit, it break the chemical bond. So if you have a DNA, it may break by X-ray or gamma ray or ultraviolet light. When frequency is below infrared and microwave, the energy level is always less than this So when those EM wave hit the electron, it get excited but stay within the well, and it's never break the molecule. Okay, so you have to understand this very important characteristic. This is energy, not by bunch of photons or EM wave. Photon and EM wave, same thing, right? So this is for single EM wave. EM wave is quantized. Okay, so that's the EM wave, and you know the full spectrum of EM wave. It goes gamma ray, it's a high energy, X-ray, ultraviolet, and visual light, and infrared. Then we have a microwave, and we have those TV, mobile device wave. The mobile device getting into microwave range right now. This frequency is increasing, but way below visual light. Okay, the another characteristic is this low frequency. The wavelength is so long, and person standing here is not going to stop that wave, because wave is far longer than the human body. It's propagate through. Okay, when it's coming to this microwave, wave becomes like a milli wave. The milli wave is not going to go through human body. It's going to bounce back, and only small amount is absorbed by the skin. And same as infrared. When you get feel warm from the fire, it's mostly infrared EM wave hit the skin and absorb a little, mostly bounce back. Beyond this frequency, it's going to be very high energy, and it may interact with molecule in the body. Okay, so that's a characteristic of EM wave. Okay, so, and this is the typical radio or mobile device communication. What they do is carrier. The carrier is much higher frequency than actual data on it, and the reason is they extract the data from the carrier. So carrier can carry multiple data, and depend on how you modulate, they call it modulation. The data is modulated into the carrier wave. Carrier wave can be sinusoidal, the sine, cosine curve, and that's change the modulation mode. They have like AM, old radio, FM, and the digital modulation method. So the carrier carry the data by EM wave. So the like a voice is very low frequency, like a 50 hertz to 2000 hertz, and that's going to be modulated into say 50 megahertz. Then it's propagate out to the space, and antenna pick it up and demodulate in the radio unit to extract the voice. Okay, so that's the electronics majors, they will learn this whole process of how to do this. Okay, I hope you enjoyed this video, and please check other videos, and if you like, subscribe.